Firelaser works by forming a very thin stream of fuel and igniting it with an electric arc. It's fully self-contained with a battery, fuel tank, and pump. It's basically a mini precision flamethrower, but looks vaguely like a lightsaber. As with all of my projects, after the first version I always come up with new ideas for a second. Basically a never-ending arms race between me and myself. For Firelaser, the biggest thing I wanted to fix was the wind issue. The flame was incredibly susceptible to even slight breezes. There isn't any way to completely solve the wind problem, at least not without switching to a completely different type of blade or using very exotic fuels, but there are ways to make it better. What I did find when testing the previous version is that higher fuel pressure tends to result in a more stable flame. To get higher pressure, I need to completely redesign the pump. The old pump used rollers to squeeze a flexible tube over and over to pump fluid along. This is called a peristaltic pump, and they are quite common when it comes to pumping chemicals, like fuels or solvents, since there's no seals to potentially leak. The pump needs tubing that the rollers can squish closed to form a moving seal to pump the fluid, so the tubing needs to be quite soft and flexible. The downside is, it's so flexible that under high pressure, the tube itself starts to expand and leak around the fittings. I previously fixed this in the old pump by using small clamps to keep the tube from popping off the fittings. But even with the clamps, it still couldn't go much above 30 psi without starting to leak. For the new pump, I wanted to make sure I could reliably reach higher pressures and flows to produce a more resilient flame. Instead of trying to find a way to get a peristaltic pump to work, I'm going to revisit one of my older designs that I couldn't get working the first time, something called a diaphragm pump. Diaphragm pumps are common in industrial applications for pumping harsh fluids since they have no moving seals. Hence, catastrophic leaks tend to be pretty rare, which is perfect since I'd prefer to avoid spraying fuel all over my hands when I'm using it. The industrial pumps are usually air-powered. They have two flexible rubber parts on each side which are called the diaphragms. The outside of each is in contact with whatever fluid you're trying to pump, and the inside area is where the pressurized air goes. A valve alternates which side gets pressure to make the diaphragm move back and forth. That motion, along with some check valves, is what pumps the fluid. Obviously, I don't want to hook up an airline to run my pump, so I'm going to move the diaphragm with a motor instead. Previously, I tried making check valves by using just a drilled hole as the sealing surface, but they leaked so bad that they might as well have not even been there. I spent quite a lot of time on various pump designs, but they all suffered from the leaky check valves, which is why I eventually gave up on them and switched to the peristaltic pump. This time, however, thanks to some comments on the video of my last version, I'm going to attempt to seat the valves into the pump housing by lightly tapping on them. In theory, the soft aluminum that the pump is made out of will deform a tiny bit and leave behind a surface that perfectly matches the ball. Another issue with the older pump versions was making good diaphragms. At the time, I was still planning on using acetone in the fuel mixture, and finding a material compatible with both acetone and the other ingredients was nearly impossible. The only options were exotic plastics like FEP or Teflon, neither of which were stretchy enough, so I had to make weird designs to try to get it to work. Eventually I found a replacement for acetone which allowed me to use Viton tubing, which is what the final pump for the previous version used. I'm able to get thin sheets of Viton as well, so that is what I'm going to try using for these new diaphragms. But before I get too carried away, I'm going to make a small simple prototype to make sure everything works the way I expect before designing the entire thing. Amazingly, I finished assembling the pump and it actually worked, which is already a big improvement over all my previous diaphragm pumps. Now that the proof of concept works, I can make a full design based on the prototype. With just one diaphragm, the pressure output is very inconsistent since the pump is only outputting fuel for half of the rotation. To fix this, I put 8 of those single pumps all around the crankshaft so they will pump in sequence, giving a smooth and consistent output. Along with redesigning for the new pump, I also redesigned the entire layout. This new version uses a larger tube which allows me to fit much more stuff inside and gives more freedom in what parts I can use. Even though I'm trying to make all the parts as reliable as possible, I'm sure there are still going to be issues, and if it isn't going to be reliable, it should at least be easy to fix, which is why both of the parts that connect to the main tube are threaded so I can easily gain access, along with some fancy methods of getting fuel and USB power through rotating connections, so I don't need to worry about connecting and disconnecting wires or tubes every time I take it apart. There's a lot to go over when it comes to this entire electronics section, and I want to keep this video a reasonable length, so be sure to subscribe so you don't miss out on that future video. In the meantime, let's get back to the pump. Usually I machine all of the parts for my projects by myself, but because the main part of the pump is so complicated, and I no longer have a fourth axis for the CNC, I wasn't looking forward to it. Luckily, PCBWay reached out and was willing to sponsor a video. I actually have already used their PCB services, but this was the first time I've ever tried their CNC machining. I simply uploaded the part files, selected the material along with a couple other options, and hit order. They also offer 3D printing, sheet metal, and PCB assembly services, so you can get everything made in one place. A few weeks later, all of the parts arrived, and I was surprised how well they turned out, considering how much of a nightmare they must have been to machine. I also got all the PCBs I need, which I'll go over in more detail in the next video. Be sure to use my link in the description. New users get $5 off their first order, and it helps support my channel. I ended up still machining the valve caps myself since I knew I'd need to make some small adjustments, and they were much simpler so it didn't take too long. I machined all of them, but only drilled the flow paths on one so I could verify it worked before I potentially scrapped all of them if it didn't. I used the same method as in the test setup to make valve seats for the balls to seal against. Only this time I went a step further and made a tool for grinding the valve seats. This is done professionally for the valves and engines, and I got valve grinding paste made specifically for it. But it ended up being way too aggressive for these small valves. I found some much finer paste and gently ground the seats to do my best to get the best seal possible. The grinding made a noticeable difference in the before and after finish of the valve seat. It's much smoother and more uniform, which should result in a better seal. Because these valves are so small, I couldn't find anywhere to buy small enough preload springs for them, so I also need to make those. I usually do this on the lathe, but since I need at least 16 for all of the valves, I decided to have a go at automating it. I threw together a quick G-code program to wind 2 at a time on my CNC mill instead. Now with hopefully the best valves I've ever made, time to see how well they actually work. I assembled the new pump but only put one finished valve cap on. The others are just blank so I could test the one by itself. With the new pump fully assembled and one pump element working, I measured the flow rate by counting how many rotations of the input shaft it took to move a known amount of fluid, in this case the size of that syringe. The resulting flow was about 70 microliters per pump rotation, so in theory, with all 8 of the pump sections installed, it should output about 8 times that, which is 560 microliters per rotation. This all looks promising, so I'm going to move on to trying with all 8 pump sections. After finishing the machining and grinding on the rest of the valve caps, I fully assembled everything and ran the same flow test again. But this time I got some really strange results. Even with all 8 sections working, it was only pumping about twice as much fluid as the single section. This didn't make any sense, so I pulled off all the valve caps and tested them individually to make sure none of them were leaking or stuck open, and they all seemed just fine. Maybe since it's not fully assembled and a support bearing is missing, the drive shaft isn't being held in line very well. The crank responsible for driving the pistons is trying to resist being bent out of position due to the load of all the pump sections. With just one section working, there wouldn't have been all that much force, but with all of them installed now, I think it might be too much. The pump is supposed to have 2 bearings supporting the input shaft. One is installed up at the front, but I never installed the other one since I hadn't made those parts yet. I probably should have realized this was an issue due to how much the pump was shaking around when being driven. Any movement that's going into making the pump shake isn't going into the pumping action, so this could definitely be reducing the expected flow. To fix this, I assembled the final motor and electronics and attached it to the pump. This way the pump shaft is properly held in place, and also has the final motor I plan on using to drive everything. This way I'll be able to test exactly how the final assembly will perform. With the new motor and everything properly assembled, I'm definitely getting more flow. However, when I calculated the expected flow rate, it was still way less than it should have been. The reason it seemed like I was getting so much more flow was just because the pump was running faster than before. But after accounting for that, I'm still getting a lot less than I should be. I noticed while testing that when the pump starts, it initially has a very high flow rate, but it quickly drops down to barely anything. When I investigated further, I saw that the pump was not only pulling in liquid while it was running, but even after the motor had stopped spinning, it would continue to draw in a bit more fuel. This led me to think there was a restriction on the inlet somewhere. A restriction would make it so no matter how fast the pump went, or how many pumping elements I had working together, only so much liquid could be sucked in. If this is the issue, it makes sense that after the motor is shut off, the liquid finally has enough time to catch up and reach all the diaphragms, making it so on the next startup, all the diaphragms are full of fuel and can pump at the full expected rate, but only for one cycle before they'd be starved for fuel again. I knew the tubing connections and inlet holes in the pump were quite small and would eventually be the limiting factor on how fast it could pump, but I didn't expect to run into the issue so soon. With some quick tests pushing the target flow of fluid through those same tube and fitting restrictions, it only takes about 2 psi, which isn't much, so something else must be going on. If everything leading up to the pump is good, then the problem must be inside the pump. The fuel comes into the pump through this fitting, then spreads out to each pump section by going through these slots and angled holes. When I took apart the pump, I noticed that the rubber seemed to be getting squeezed down into those small slots where the fuel was supposed to come in. When I tighten down the valve caps, a small amount of the rubber gets squished out from around the edges. This is fine since it means everything is sealing properly, but I think it may also be happening on the inside, which isn't as good. If the rubber is getting squeezed into those slots where the fuel is supposed to feed through, it could end up partially blocking and limiting the flow. I decided to test cutting out an area in the rubber for that slot so it would stay clear. I briefly tried modifying one of the existing diaphragms by hand, but quickly realized I should just leave some stuff to robots, so I lasered out the new ones instead. The new diaphragms leave an opening for the entire length of that slot to avoid restricting the flow as much as possible. I replaced all of them and once again ran a flow test. It is a little better than before, but still less than it should be. It still has the same issue where it continues to draw in fluid after the motor stops, and has a significantly higher flow rate right when the pump starts. Maybe the diaphragms themselves aren't moving as far as they should be. If we look at the 3D model, you can see where the diaphragm connects to the piston and where it is held in place by the valve cap. Just imagine the diaphragm stretching as the piston moves, since I do not feel like modeling it flexing. At the top of the stroke, the rubber is being pushed by the entire piston face, so there really isn't anywhere for it to go and all of the fluid above it is forced through the outlet valve. At the bottom of the stroke, I'm relying on this washer and screw to hold the rubber to the piston head. There needs to be some unsupported space between the washer and cylinder wall to allow the rubber to stretch and flex so the piston can actually move. I was hoping the stretchiness of the rubber would cause the area to be pulled tight when the piston moved down, preventing the suction from pulling it in too much, but because of the flow issues, I'm going to fix it just in case. If the edge of the diaphragm is being sucked in instead of the fuel, then the output flow would drop. It makes sense that if all the diaphragms were being stretched in like that while the pump was running, it would take some time after the pump stopped for them to pull back to normal and bring in the remaining amount of liquid. I'm going to make a new piece that replaces the washer and holds the rubber much closer to the edge. That way it'll be pulled tighter and not be as easy to get sucked in instead of the fuel. I preemptively cast both the new washers and new pistons out of high-strength epoxy instead of just using the SLA printed parts to make sure they wouldn't break under high pressures. I still had to do some machining to drill the holes for the pins and make the threads, but casting the parts made it much easier than machining the entire thing from scratch, especially with very small and intricate parts like this. The washers were so small and thin that I ended up making a little vacuum chuck that sucks them down in place so I can machine them without needing to try to grab them in a vise. When I took apart the pump to change them out, I found some of the old SLA printed pistons already had their threads totally stripped out, so it's a good thing I switched to the new cast ones. I wonder if those stripped pistons were also contributing to the low flow rate. The new pistons are definitely stretching the diaphragms more than the old ones. There is much more resistance when I turn the pump, which worries me a bit since I don't want to end up stretching them too far and damaging them, but I'll worry about that if it becomes an issue. I was kind of afraid to really push it and see how much pressure it could produce, so I only went up to about 80 psi, which is still 3 times higher than what the last version usually ran at. However, after testing for a while, I still managed to break it. Under barely any load, I heard a snap sound come from the pump and then the flow rate dropped. Oh no. This time it was because I never ended up upgrading the main part that drives all the pistons, and it was still the original 3D print, which had finally decided to crack. I probably could have cast replacements like I did with the pistons, but I instead went straight to machining the new ones out of aluminum. While everything was apart anyway, I also switched to the final pump body. I ordered two so that I would have a backup. The only difference on the second is that it's sized for me to be able to cut threads into it so I can thread the outer tube onto it. I used the CNC machine with this tool called a thread mill. I threaded the new pump body and outer tube and they look great, but they don't thread together well. There's one major problem with using aluminum threads. Aluminum is prone to something called thread galling. This is when the threads in contact with each other tend to stick together. Small areas are being cold welded together, causing little globs of material to form and damage the threads. As you continue to thread the parts together, the globs continue to grow. Usually by the time you can feel this, the act of even trying to unscrew the threads can be enough to completely destroy them. This exact issue is why anti-seize exists, and is often used on stainless steel and aluminum, which are both very susceptible to galling. Those of you who have worked with anti-seize know it gets absolutely everywhere and is a mess, so I went with anodizing instead. This process produces a hard oxide layer over the aluminum much tougher than the thin coating that forms naturally. I anodized both of the parts I plan on threading into the tube, and the threads now fit great. After moving everything over to the new pump housing, I think there's still one more suspect that might be holding back the flow. Remember those springs I wound way back at the beginning? Well, I kinda just guessed how stiff they needed to be. While going through the test results, I saw it was still way underperforming, so I finally did some calculations to see how stiff the springs should be. Turns out the ones that are in it are putting way more preload on the valves than needed. This would explain the flow restriction issue I've been having, so I rewound much lighter springs and swapped them all out. Time to see how well all of these fixes work. After getting the pump fully primed, the flow at no load was about 30% better than the old springs, and 10 times better than the old version. Flow is only part of the equation though. The previous pump could only reach about 30 psi. I know the new one should be able to reach at least 80, but the question is how high can it go before something breaks? For all of these tests, I have the pump hooked up to a pressure gauge with a valve so I can restrict the output. I slowly closed the valve to see what pressure it could reach. It maxed out at 140 psi and actually survived the test without breaking anything. That's almost 5 times the pressure of the previous version. This opens the door to much stronger streams that should be more wind resistant. With the new pump working comes the next two challenges relating to moving the fuel around. How do I store the fuel before feeding it to the pump? And how does the fuel get into the super thin streams needed for the flame to work right? Storing the fuel was super easy compared to everything else. Last time I used the outer tube as the tank and had a sealed plug that could slide in and out as fuel was pulled out by the pump or filled up through the fill port. This time though, in the spirit of not having any seals that could leak fuel all over me, I'm going to revisit the collapsible plastic tank idea from the last version. I got one of these cheap heat sealers used to seal plastic bags shut. It has a metal strip that it heats up to melt a thin section of plastic together and make a secure bond. All I did was seal up some strips of polyethylene plastic, which is the same thing these black garbage bags are made of, and attach this metal connector that allows me to get fuel in and out of the bag. I tested the plastic with a small amount of fuel to make sure it could survive without deteriorating. After a few days it seemed about the same, so I think it'll hold up just fine. It then gets rolled up so it can fit inside of some tube and is attached to a brass fitting on the end to act as a new fuel port. Instead of using a large syringe to fill it like the old version, this one lets me completely take off the tank and either swap it for a full one or refill it. Finally, there's the output after the pump, which is much more challenging. The key part of this entire project is the nozzle. I'm going to go more in depth with the nozzles in a future video, but the basic requirement is that it needs to be a very small hole, only about 3 thou in diameter, which is about the same size as a single hair. Before the fuel makes it to the nozzle, there is one more critical part. Since the nozzles are so small, they are very susceptible to clogging. Even dust in the air is enough to plug them. This was a big issue with the previous version. Not only did it clog constantly because it didn't have a good filter, but it was really hard to clean the nozzle if it did clog, since the igniter electrodes were permanently attached to the wires such that everything needed disassembled to get access to the nozzle to clean it, only for it to clog again a few minutes later. For this version, I made a larger filter to handle both the increased flow of the pump and prevent the filter itself from filling up with debris too quickly. It sits in front of the pump where each of the sections outputs fuel. The main layer is this chemical resistant felt that can filter particles all the way down to 5 micron, which is more than enough since the nozzles themselves are around 76 micron. The second layer is some fine stainless steel mesh, which isn't actually for filtering out dirt, but is for keeping the fibers from the previous filter getting sucked into the nozzles. I did some testing with a set of nozzles that ended up being a bit too large, so there wasn't quite enough restriction to build up decent pressure, but I was still able to run everything for a while to make sure it all held up properly. It still needs the electric arc to ignite the fuel, which I haven't finished yet. The next video for Firelaser will be the full final assembly and testing to get the best flame I can out of it. If you made it to the end of the video, be sure to subscribe and join the Discord to keep up to date on projects. Thanks for watching.